Very excited to share with you the research that Michael Biercuk has been presenting. So let me introduce you to the final keynote today, Quantum Computing, Australia Leading the Way. Professor Michael J. Biercuk is the CEO and founder of Q-CTRL, a venture capital-backed company that provides disciplined control engineering solutions to harness the power of quantum physics for next-generation technologies. Q-CTRL is built on Michael's research leading the Quantum Control Lab at the University of Sydney, where he is a professor of quantum physics and quantum technology. Michael holds both CEO and professorial positions concurrently, and in his academic role is a chief investigator in the Australian Research Council Centre of Excellence for Engineered Quantum Systems. An award-winning experimental quantum physicist, Michael speaks with clarity and authority, as we'll see today, about science and technology, and is adept at making physics accessible for a lay audience, such as with his TEDx Sydney performance in 2016 and articles in publications such as ABC Science, The Conversation and the Australian Financial Review. Michael enjoys working at the intersection of science, technology, watchmaking and fashion, and can make difficult concepts entertaining, from what electricity is to how computers work. Michael is one of the world's leading experts in the new emerging field of quantum technology. The work he is doing promises to be as transformational in the 21st century as harnessing electricity was in the 19th. He is also an active creative collaboration with luxury watchmaker R. Lange and Cerner, focused on the links between high horology and quantum physics. Please welcome to the stage Michael Biercuk.
Thanks. Well, thanks for having me. That was a bit of a verbose introduction, but I appreciate all of the background being presented. I'm really grateful to be here to get to speak with all of you. I am fully cognizant that I stand between you and beer o'clock, so I promise that through this presentation, I'm going to do my best to focus on actually providing you useful insights and not just telling what might hopefully be a fascinating story. You heard earlier today about new kinds of technology that have the potential to impact and shape your jobs. New kinds of technology that get thrown around like blockchain and AI, machine learning and the like. I want to tell you about one of those that's clearly been in the media a lot of late. That's quantum technology. And in particular, I want to tell you about the role that Australia has played in bringing this new industry to reality. You heard about my kind of CV. I run an academic research lab at the University of Sydney. I'm also the founder and CEO of Q-CTRL, which is Australia's first venture capital-backed company in quantum technology, based in part on the research that my academic group has done. But today, in addition to telling you about that background and that kind of fun story, I want to give you specific insights about what quantum technology is and how it's going to impact, or how it's most likely to impact, the kind of work that all of you do on a daily basis. And as you heard in the introduction, we're really excited about this because we do legitimately believe that this new kind of technology, quantum technology, which harnesses quantum physics as a resource, is likely to prove as transformational in the 21st century as harnessing electricity was in the 19th. And I don't mean this just because it's new and shiny and we all get excited about the newest thing. I mean it because there are deep parallels in the way we learn to access and then harness a new resource in the flow of electricity, and how we're doing the same thing today, learning to access and harness the physics that comes to us from quantum mechanics. Things that we hear about in the popular press, like superposition and entanglement, quantum strangeness. If that sounds a bit overblown, it's useful to look around at what exists today. The first quantum technology, the first thing that we've ever built that truly exploits this kind of phenomenology, it's already absolutely changed the world. And in fact, it's probably shaped most of your days. Global positioning systems work because of atomic timekeeping. And atomic timekeeping fundamentally uses as a resource quantum superposition. It uses quantum superposition in order to access the very stable tick inside of atoms. Having access to that tick is what allows us to do geolocation within centimeters. That's what gives us location-based services. If you came here via Uber or Waze or Lyft, this already shaped your day. If you used a conference calling technology, have a wide area network that's synchronized, it's synchronized based on GPS. This is just the first application, and think about how much impact this has had. What's really exciting from the prospect of building a new industry is to look ahead and to do like a total addressable market analysis and think about how much potential impact this new field can have. If we look across different verticals, different parts of the economy where quantum technology is mooted to have impact, the numbers really grow to astronomical levels very quickly. We can start with something like quantum computing, which I'll tell you about today. This is the idea of applying this new physical resource as a means to encode and process information, mooted to be as large as the supercomputing industry is today. But we also have things that are not maybe talked about as much but are equally impactful and large. Things like defense sensing for aerospace, sensing underground hardened targets, anti-submarine warfare, minerals exploration, and also medical imaging, new kinds of magnetic resonance that leverage the physics that I'll be telling you about today in order to give insights that are not accessible with today's technologies. Now that's a pretty enormous number, that $100 billion number. And that brings us to an appropriate segue, which is to acknowledge that in 2017, one kind of quantum technology, in particular quantum computing, made it onto the Gartner hype cycle. And so we can all like cheer and be excited for that. Of course, we're excited because it's still on the innovation trigger and is not transitioned over to the trough of disillusionment. But this kind of context, I think, is important. I think it's important to recognize the field, warts and all. Because when we look back in history, we see that you can only talk about this kind of technology appearing on something with as high a profile as the Gartner hype cycle after having been through many decades of fundamental research. And Australia in particular has made investments in this research discipline, in the fundamental science powering quantum technology, in a way that few other nations have until very recently. Going back to the 1990s, we saw major research initiatives starting across Australia that have blossomed into real centers of strength, in particular in Sydney, but of course all over the nation. So in Sydney, we have the University of Sydney, where I'm a professor, also large programs at UTS, UNSW, and Macquarie. It's been decades of fundamental research, of basic science, learning about quantum physics that bring us to where we are today. And fortunately, we're not only doing kind of a handover from academia to industry. There's continuing investment in the kinds of basic science and technological training that are likely to make this industry bloom in Australia. For instance, the New South Wales government announced just a couple of months ago that it would be funding a doctoral training program that is a special high-tech PhD program with augmented training, so it's a longer PhD, jointly run by these four universities, led by the University of Sydney, called the Sydney Quantum Academy. And this is an enormous part of the realignment of resourcing in this sector to incorporate not just fundamental science, but also research translation to industry. And that brings us, of course, to Q-CTRL. Q-CTRL is the company that I founded in 2017, based on the research my academic team has done in a discipline called quantum control engineering. Control engineering is the discipline that makes everything work. It makes airplanes fly, makes walking robots. We specialize in how you can put this kind of science to work to make quantum things do useful tasks. That's our goal. Because if you look back in history, you see that whole industries have been built by control engineering. Many of you are probably familiar with the Wright brothers being the first to fly. They were not the first to fly. They were the first to achieve manned-powered controlled flight. And that distinction is important because they joined an already flourishing industry of people successfully building aircraft. But they succeeded where others could not because they brought concepts that we would today call control engineering. Concepts like three-axis control, roll, pitch, and yaw. That was a totally new concept at the time. Similarly, deformable airfoils. Totally new concept brought to us by control engineering. They succeeded where others could not through control. Play the tape forward. You see the same story unfolding with autonomous vehicles, with walking robots, as I mentioned, with drones. Those quadcopters have been around for decades, but it's been recent developments in control engineering that have made them ubiquitous and so exciting, such that, even Uber is talking about air taxi service using that drone kind of technology. Q-Control is positioned to do exactly the same thing, to build a new industry in quantum technology based on our expertise in quantum control. And our list of customers and partners helps justify this. We have partnerships with some of the largest technology corporations in the world focused on this area. IBM has been a real leader in this. We're part of the IBM Q network. And while we take these things with a grain of salt, it's been very exciting for us as a Sydney headquartered organization to have been named number one. Oops, sorry, I went backwards. To be named number one among a set of the top quantum computing startups to watch in 2019. That's a global list. That, of course, has all contributed to the set of investors that we've attracted. These investors are not just local shops. These are global investors, right? So our seed funding has come from Data Collective, which is a deep technology investor in Silicon Valley, Sequoia Capital, one of the largest, most successful enterprising VCs in the world, Main Sequence, which is an Australian-based VC, and Horizons Ventures, which is the private family office of Mr. Li Ka-shing in Hong Kong. We've been really excited to attract this kind of attention. And we're grateful that these kinds of organizations are paying attention, not just in the Valley, but also here. But it's worth at this point asking why. Why do they care? Why does Sequoia Capital care about what we're doing? And to answer that, we should take a step backwards to understand what quantum technology is. And the starting point is here, in something we occasionally call the first quantum revolution. This is a photograph of microprocessors. These are the fundamental devices that we use to encode and process information. They're in your laptop, they're in your mobile phone, they're in your dishwasher, there's about 8 of them in your car. This is what has built the modern information age. These are devices that allow us to encode and process information by controlling the flow of electricity. And they're powered by a kind of material known as a semiconductor, the most famous of which is silicon, which works because of quantum physics. Semiconductors can either behave like an electrical conductor, like a wire allowing electricity to flow, or they can behave like an insulator, blocking the flow of electricity, depending on the application of another electrical signal. Controlling the flow of electricity with electricity is how we build these devices. And it comes to us because of our understanding of quantum physics. That's why semiconductors are semiconductors. These are things where we can put literally 1 billion active switches, transistors, the fundamental logic units in these devices in an area the size of your thumbnail, 1 billion. This is kind of the peak of modern technology. But as incredible and as profound as this technology is and has been, it really represents only the most rudimentary level of control over the quantum realm. The way we build these devices in the trillion-dollar semiconductor industry is, by analogy, a little bit like this. We start with a giant pile of stuff, and by learning the right rules, we shape it to the form that we want. Here we start with a giant pile of sand, and by learning the right rules, how wet does it need to be, etc., we can build magnificent forms. Here, Freud with the patient on the couch. Just like you can build something as magnificent as 1 billion transistors etched into the surface of a chip the size of your thumbnail. But it shouldn't escape your understanding that if instead of looking at the giant pile of stuff and thinking what we can build with it, if instead we were able to look more closely, we would see that there's a new level of complexity that was hidden from our view before. You see that instead of a homogeneous tan, some of the grains of sand are white and some are dark. Some are transparent, some opaque. Some are seashell, some are stone, some are rough, some are smooth. None of that was visible when you only look at the giant pile. And by analogy, we're now thinking about building technology by looking at the individual grains of sand. By looking closely enough at matter that a new level of complexity emerges. This is the second quantum revolution. This is where we go all the way down to the bottom and start building technology from the most fundamental constituents of light and matter, individual atoms and photons. And because we can look on these very small size scales, a new level of complexity emerges. This is the complexity given to us by quantum physics, the physics of very small things. And before any of you scoff at the notion of starting to build technology using this cartoon representation of an individual atom, let me show you this. This is a photograph from my laboratory of one atom. It's an atom of ytterbium. We shine a laser beam on it, and the light bounces off. If it's just the right color, we take a photograph. Take a picture just like with a camera in your mobile phone. That atom is trapped in space. It's floating in space in a kind of electromagnetic bottle called an ion trap. That's one atom. That's our individual grain of sand. And this is where we start building new technology, because there is new complexity here. When we talk about matter on these size scales, the familiar picture of nature, or of maybe the concept you have in mind of an atom, like a billiard ball that bounces off the walls of its container or off its neighbors, that picture breaks. And we have to replace it by a picture in which we conceive of atoms more like waves. Waves that spread out in space through something known as quantum superposition. Waves that interfere with each other or with themselves, like ripples in a pond. And on these size scales, nature even looks like it has its own form of magic through something called quantum entanglement, whereby particles that are linked together and obey the rules of quantum mechanics can become entangled such that if you separate them the distance of the known universe, manipulating one still instantly affects its partner. This physics is very different than what we experience. You're sitting in your chair. You're not in your chair and all other chairs at the same time. And for a long time, these concepts were thought to just be strange math. Even the greatest minds of the 20th century scoffed at the notions that were implied by quantum mechanics. Notions that in the vernacular we'd say are being in two places at once, or things like that. Einstein famously called entanglement spooky action at a distance, because he thought it was ridiculous. And he wasn't alone. Many of the great leaders of thought of the 20th century more or less tried to relegate the strange things predicted by quantum physics to the dustbin of mathematical curiosities. But in this particular case, Einstein was wrong. Because going to the 1980s, we started building technologies that allowed us to see the individual grains of sand. This is the ion trap that exists in my lab. This is how we confine one atom in an electromagnetic bottle. It's the kind of technology that won my former supervisor, Dave Wineland, the Nobel Prize in 2012. Once we could see the individual grains of sand, we could explore the new complexity that we found. And what we discovered is that every weird thing that quantum mechanics predicts is true. As counterintuitive, as different from our daily experience as they may be, they're all correct. No other theory has accurately predicted something where quantum mechanics has failed. And the next step is putting this to work. We have something new and validated, and our community is now looking to build a new class of technologies. These are quantum technologies. The one that I'm going to focus on for the rest of this talk, because I think it has the most bearing on your interests, is quantum computing. Who's heard of quantum computing? Great. The first message that I want to give you about this, the one thing that you should remember if you forget everything else, is that quantum computing is not just more and better computing. You're not going to have faster Facebook. It is a fundamentally different way of processing information. And quantum computers are sometimes described as being as different from a conventional supercomputer as supercomputers are from an abacus. Now, I know that's a very visual representation of power, but it really is more about how different these things are in terms of their operation. But from a practical perspective, quantum computers allow us to solve problems that are either practically or fundamentally impossible and inaccessible, not just for today's supercomputers, but in some cases for any conceivable supercomputer we could ever build. As an illustration of how, let me give you this one simple example. This is an image from a technical research project I was involved in a few years ago. Each blue dot in that background is one atom, just like I showed you before. There are about 335 atoms in this picture. Obviously, the top of it is cut off. With 300 atoms, what we can do is treat each one like the quantum analog of a bit in a regular computer. It's called a qubit, a quantum bit, because we're not very clever at naming things. Each qubit can be 1 or 0, or in the vernacular, in air quotes, both at the same time. So the rules of quantum superposition and entanglement say that with 300 atoms, we can simultaneously represent all 2 to the 300 possibilities of how each atom takes a 0 or 1. 0, 0, 0, 0, 0, 0, 0, 1. 0, 0, 0, 0, 0, 1, 0, and so on. All of those possibilities all at the same time, in air quotes. Now, 2 to the 300 is a pretty big number. 2 to the 300 is about 10 to the 100. That's a Google. That's a number so astronomically large that if you tried to write down all of those possibilities, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, etc., in a regular computer, you would run out of matter in the universe before you could write down that number. And yet you get the same computational capacity from a system that was about a millimeter in diameter, about a third of a millimeter, actually, because of the way that things behave quantum mechanically. Now, there's a trick. The trick is, it's really hard to do anything useful with all of that information capacity. And that's the task of algorithm designers. In our community, there's a great collection of experts who focus on saying, well, now we have this new computational resource in terms of entanglement and superposition, and we can, in air quotes, do all these crazy things representing all these numbers at the same time. How do I do something useful with that computationally? It is, unfortunately, an extremely difficult problem. And this has maybe been one of the weakest areas of development in our field. All the same, we've seen major advances in the application of quantum computing technology for problems in optimization, in unstructured search, so searching needle in a haystack kind of problems, problems in material science for energy, chemical dynamics, machine learning, and one thing which maybe you've come across before, which is information security. Because this entire field in quantum computing came to us from a math problem. And the problem is the following. If I give you a number, I want you to tell me the two numbers divisible only by 1 and themselves, they're called prime numbers, that you multiply together to get that target. So if I tell you my target number is 15, I ask you, what are the prime factors of 15? 3 and 5. You're very good at this. That's great. Let's do another one. What are the prime factors, the two numbers divisible only by 1 in themselves, that you multiply together to get 21? Yes, one more. One more? Okay. How about that? Now you laugh because it looks ridiculous. But the reason that most of you were able to answer my previous two queries is that you memorized the answer when you were kids. We all memorized multiplication tables. This problem is not just hard for us. It's hard for computers. In fact, this problem is so hard for computers that the task of taking that number and finding its prime factors is the basis of effectively all cryptography that we use today. Who here has an RSA token somewhere in your bag, right? The security in that system comes because it's really, really hard to solve that math problem for computers. Anytime you do e-commerce, if you run an online banking portal, everything comes from the difficulty of that math problem. And then in 1994, this guy named Peter Shor, who was at the time at AT&T Labs and is now at MIT, said, if you can give me a machine that obeys the rules of quantum physics, that uses superposition, things in more than one state at once, and entanglement, this linking of particles together, I can write down an algorithm, he's actually written it there, that will make that problem not hard for computers. This was the birth of what's now called Shor's factoring algorithm, and led really to the advent of the entire field of quantum computing. Because in response to the publication of this paper, the US intelligence agencies stood up their first ever university research programs. First time the National Security Agency, the three-letter agency that everybody's most afraid of, funded university researchers to answer the question, is it possible to build this computer? And now you play the tape forward to today. My team, which has been funded by the NSA since the, well, my own team since 2009, but previously when I was a grad student in the early 2000s, funded by this agency. Australia really getting its start in this field because the NSA invested really, really early at the University of New South Wales and University of Queensland. Play the tape forward to today, and the answer is the affirmative. We can build these machines. And right now you see a transition from academic science answering the question, can we build these machines, to major industry investing and trying to make this a commercial reality. Just in the last few years, some of the biggest technology oligopolies in the world have made major efforts and investments in quantum computing. Including here, Microsoft has a major investment at the University of Sydney, my colleague David Riley. This is a change in our community. The time is now for this to really come to reality. At the same time, we see both technology push and application pull advancing the underlying hardware. New problems coming within reach. Major developments in the operation of quantum computers. I run one in my academic lab. Anybody wants to come and see it, let me know. We also see a new SME-based, so small, medium enterprise-based industry blooming, in this case in Australia. I've told you about Q-CTRL. We're not the only company active in this space. We're kind of unique in what we do. But QBranch is a data analytics firm. HBAR is a consulting organization. They help companies understand what's going on here. Liquid Instruments, Quintessence, Mog Labs, they all make hardware associated peripherally with this field. The time is now for investment and engagement with this particular field. And really the last pillar for this argument is that end users are really getting active. These are not names that you would typically associate with deep technology research in quantum computing. And yet these organizations are all engaged with IBM or Google or others through various networks. In this case, these are companies from the IBM Q network. We're a startup in IBM Q. We're a provider to IBM. These are the end user customers of IBM, right? They're from on the other side of the network. And they are all, in many cases, paying dollars right now to access toy quantum computers. Because these systems are really available. This is a photograph of an older generation IBM system. That's a real quantum computing chip that is accessible on the cloud. This particular one is accessible for free. There are others that are paid access. Now, I want to emphasize these are toy systems. But all of those organizations I showed you a moment ago are excited to become what's sometimes called quantum ready, prepared for what's coming in this industry. There is huge progress in this field. But it is also useful to contextualize where we are, because I'm sure many of you have heard kind of sky is falling articulation of what's happening with quantum computing. Well, right now we are right there in the middle. The biggest quantum computers that are operational today are between 20 and 50 so-called quantum bits, these fundamental carriers of information in quantum systems. Remember how we started this journey, 1 billion transistors in an area the size of your thumbnail. That's 50. 50 is a lot less than 1 billion. But you'll see why that doesn't matter as much. Now, we expect that in this next 8 to 10 year time period, we'll be getting to systems of about 1,000 quantum bits. And with 1,000 quantum bits, we think we can really solve interesting, exciting problems of relevance. Organizations have become so excited that here, two big names among the tech oligopolies have entered a kind of marketing PR race about two competing terms, one called quantum supremacy and one called quantum advantage. Has anybody heard of either of these? You are well insulated from the media because this is all I ever hear about. These are terms that, now if you were in the session about kind of cognitive dynamics, now that I've said them, you're going to hear them everywhere. Quantum supremacy is favored by Google, quantum advantage favored by IBM, both organizations mooting that in the next, say, 5 to 10 years, it is expected that these significant milestones that I'll articulate in a second will be achieved. The high-level explanation of these two things is that in achieving either supremacy or advantage, by building a device that obeys the rules of quantum physics, a quantum computer, you get an advantage over the best alternative. And what's really exciting about this field is, remember I told you about this 2 to the 300 number of possibilities? Well, even with 2 to the 50, 2 to the 49, that becomes a system that quantum mechanically more or less can't be computed, can't be simulated by really giant supercomputers. So you only have to build kind of a medium-scale quantum computer to potentially do something that's better than the best supercomputer you could access for some data analytics problem or whatever. Now I want to disambiguate between these two things for you, so you can impress people at parties. Quantum supremacy is not the same as commercial utility. If someone talks about achieving quantum supremacy, that doesn't mean that they're solving a problem that is useful to anybody. In fact, quantum supremacy is all about concocting problems that are really exotic and difficult for conventional computers, such that a quantum computer might be able to do them, but kind of no conceivable giant computer could. Now, there's a more technical definition, but this is the vernacular understanding. Meanwhile, quantum advantage is focused on solving a problem that you care about better, cheaper, faster. Both of them are significant milestones. One is a little bit more scientific and kind of scientifically profound, this idea of quantum supremacy doing something no conceivable computer could do. And the other is more commercial, giving you as a user an advantage in running a computation. And what's been really interesting is that as these small-scale systems have come to reality, as we've done technology forecasting out where we're going to be in 8 or 10 years, we've seen a new class of algorithms emerging that I think would be of relevance to you. There's a whole new field of quantum finance, quantum computational finance, because many of you, if you're engaged with or run quant shops, or you just do basic modeling for financial derivatives like Black-Scholes, or you do risk analysis, you use computational tools sometimes called Monte Carlo simulation, right? If you're not doing it, someone at your desk is doing it. This is a technique by which you more or less sample a whole bunch of random possibilities, and it's computationally very taxing. Here are papers from a company in Canada and also from IBM, looking at two different classes of problem. One, pricing of financial derivatives using Monte Carlo simulation. The other, calculating VAR and CVAR. So these are risk measures, both of which have replaced Monte Carlo with a quantum computational problem. It turns out that a lot of the trickery is how you map the finance problem to an algorithm that we know you can run on a quantum computer. Happens to be called amplitude estimation. But once you can do that mapping, now you get some of the advantages of quantum computing. And in this case, the suggestion from extrapolation of the results they have says that computations that otherwise take of order a day can be reduced to hours or minutes. And the framework that they present is the idea of doing real-time risk analysis. Instead of having to crunch overnight and then your information becoming stale before you can make an actionable, you can take action based on this information, you can in principle do real-time risk or financial derivative pricing and potentially have a competitive advantage. It's not the only area where we think quantum mechanics and quantum computing can have an impact in finance. In another area, You heard earlier today, and I'm sure all of you get beaten over the head about blockchain. Well, here's an academic paper that demonstrates that Bitcoin, in this particular case, but blockchain broadly, is not secure against quantum mechanical attacks. They analyzed the algorithm in a rigorous way, and they show that one particular part, which uses something known as elliptic curve encryption, is actually susceptible to a quantum computational attack just like RSA. And so it may be that the system that's big enough to perform this computation is quite a long ways away. But if you rely on distributed ledger that's persistent over decades, that's not secure. It's the same kind of general consideration about why governments who are currently using very challenging public key crypto systems still worry that in 30 or 50 years there may be a giant quantum computer that can crack public key crypto systems. Just a reminder, this is where we are, about 50, so don't freak out yet. You can freak out later. Because there is kind of an Achilles heel. Quantum computing has a major challenge. And that challenge is that the hardware is unstable. Because whenever we try to encode information into here a cartoon representation of an atom, over time, that information gets randomized. It interacts with Wi-Fi, with changes in the Earth's magnetic field. Everything around it shakes your quantum system and randomizes the information. And then when you take that shaken randomized information and you try to run an algorithm, you get errors. In fact, the errors are really kind of mind-bogglingly bad. In the laptop that's running this presentation or in your mobile phone, the transistors that are operating are unlikely to suffer a hardware fault where a 1 becomes a 0 or vice versa for like 1 billion years of operation. At 1 billion cycles per second, at gigahertz, right? 1 billion years, you'll never have a hardware fault. If you get the blue screen of death, it's because of software. In a quantum computer, the lifetime is about 1/1000th of a second. At the extreme end, it's about 27 orders of magnitude more likely to suffer a hardware error. 10 to the 27. This is where Q-control comes in. Q-control stabilizes the underlying hardware through something that we call quantum firmware to extend the lifetime, the useful lifetime of quantum information, and accelerate the pathway to the first quantum computers. This is the proposition that has gotten our investors so excited and so engaged. And we provide tools for the hardware manufacturers, for research teams, and also for end users to allow them to run algorithms in such a way that gives better results, results that are more robust against error. And all of this is leading us and teams like ours to try and help this transition of quantum computing from an academic pursuit into a major industry on its own. Now, I hope that the kind of applications I've talked about are sufficiently compelling. But if they're not, then I want to give you this thought. This is a picture of the ENIAC. This is the first digital electronic computer. It's the first computer ever built that actually performs computations more or less the same way we do in today's microprocessors. You encode information in ones and zeros, digital encoding. This was a system built at the University of Pennsylvania in the 1940s. And when it was commissioned in about 1946, there was only one application for this machine, and that was calculating artillery shell trajectories. Nobody at the time had ever conceived of Fitbit or Amazon Web Services. Yet these are the natural outcomes derived from access to this kind of computational hardware. The same is true with quantum computing. We have a whole new world of computational capabilities opening, and we've seen again and again that the most profound impacts of new technologies are the ones that are least anticipated. Quantum computing really promises to change the world. Q-Control is excited to help bring this to reality and to help all of you embrace your quantum future. So thank you very much. Hope you enjoyed it.
Thank you very much, Michael. So a couple of questions. What do you think the time frame is from where your research is around creating something that is stable and usable?
Yeah, I think the best predictions we have are that in the next kind of 8 to 10 years, we will be able to build a system that is sufficiently large and sufficiently stable to perform a computation that people in this room would care about.
And what, having a look at the ENIAC back in the day, what do you think the predictions are for what it's going to achieve? Do you have some ideas, being deep in it, for us lay people that have no clue whatsoever?
Well, the reality is that most of my colleagues and I also have no clue. We kind of do our best to get by. There are very clever people who build algorithms for a living and help identify what problems we might want to solve. The class of algorithms that have become most exciting to us are all in calculating problems in chemistry. Now, while it may sound a little bit esoteric and like, why does anybody care? Something like 90% of all global supercomputing time is solving physics problems. Not finance or anything else, physics problems.
Sorry, finance people.
So what we see in chemistry is that there are a lot of approximations that are made. And all you need to do is a better approximation than the best approximation. In coming up with algorithms for a long time, our community has always tried to achieve what are called asymptotic gains. If you build like the biggest supercomputer you could build and you build the biggest quantum computer you could build, you would get these giant benefits by using the quantum version. We just need to outperform kind of the computational capacity of what you can pay for, right? And that means that big problems in how we produce fertilizer, which amazingly, has anybody heard of the Haber-Bosch process? So, we use nitrogen-based fertilizer. We use ammonia fertilizer. Making fertilizer consumes almost 5% of all natural gas output every year. Because you have to take precursor chemical 1 and precursor chemical 2 and put them together under enormous pressure and temperature. Right? It's really, really hard to make fertilizer. We put all this energy into it. And yet, it's happening all the time in the roots of plants by bacteria. We don't really understand how. We have very limited insight into how biological systems do this. And it is believed that by making a quantum computational model, you may be able to solve some of these problems. Because chemistry is fundamentally the quantum interaction of atoms, right, of molecules. This is a problem that was addressed by Matthias Treuer, who's now at Microsoft. But we kind of collectively are seeing problems in chemistry as the starting point, where you get these major gains that lead to the giant investments in algorithm design going forward.
And so when it does, hopefully, become a usable and viable product, does that mean that everything that we know right now will have to be completely dismantled and we build new things?
Fortunately, no. The way we're currently conceiving of the delivery of this capability, I mean, as I mentioned, it's telegraphed by what companies are investing. That it's kind of like quantum compute as a cloud service, right? That quantum computers are good for some things. They're really good for some things and not at all good for other things. And as a result, we think about quantum coprocessors or accelerators. So any of you who deal with kind of cloud-based services from AWS or Google Cloud or Azure, you know that you can buy time for a microprocessor, or you can buy time for a GPU, a graphical processing unit. It's just like it's another option for problems that are machine learning based and maybe suited better to that hardware. We think that quantum computers for a long time will be like that. They'll be an accelerator, but the important thing is they open problems that are not accessible otherwise.
And you also mentioned that quantum computing has will potentially break distributed ledger. Is that a concern?
Depends on whether you like Bitcoin or not. I think
is it just Bitcoin or is it other?
It's all distributed ledger that uses public key crypto systems, right? So should you be concerned? In a sense, yes, if you care about the longevity of this information. In another sense, no, because the size of the machine that will be required to do this is really enormous and is a long time away. So, I mean, legitimately 20 plus years before you're worried about any system that could even come close to solving that problem. So don't freak out yet. But for those who do like long-term risk analysis and things, maybe you start investing earlier.
So I'd like to preface before I ask the floor for questions, no question is a dumb question in this session. So I know that I feel incredibly undereducated after that session.
You can talk about watches too if you want.
Yeah, you can talk about watches, yeah. Any questions from the floor? Come on, be brave, people.
Come on.
Yes, Neil, thank you.
Michael, thanks for your presentation. Just to follow up to Vanessa's last question, I mean, well, what are the risks around quantum computing, you know, if the bad guys get their hands onto quantum computers and that sort of thing? What are the downsides that you foresee in the future and the risks that we need to prepare for?
Roughly the same as, you know, giving a big stick to your nasty neighbor, right? Anything useful can be weaponized, whether it's a conventional computer or a quantum computer. And, you know, there are certain problems where you may be able to gain computational advantage with a quantum computer, but we're seeing right now the impacts that kind of very classical machines can have in terms of hacking on computer grids and things like that. In my view, there is no kind of profound qualitative difference between having access to a computer in general and a quantum computer for a nefarious actor, whether state or otherwise.
Anita.
I'm curious about the diversity in your team. You talked a lot about your team and diversity in your team, and we hear a lot about trying to get more diversity in the fields of the sciences. And I'm just curious how you guys think about that, people that are actually in the profession today.
Yeah, it varies by which part of my life you're talking about. In the quantum physics part, it's probably not what you expect. In the quantum physics part, my team is about 50-50 women and men. You know, in science, it's easier that way. In the kind of software world, it's tech bros, and there's not that many women who are working in that community. So I mean, it is a challenging issue. I think, you know, there's a giant demand for talent. Most of that demand is coming from the organizations of people in this room, and there isn't so far a big pipeline of talent behind it. So we're all competing over scarce resources. But on the quantum side, it's much better for reasons I don't fully understand.
And what kind of talent are you looking for? Like, is in demand? If someone wanted to change careers and become a quantum scientist.
We are always, of course, looking for people who are trained in quantum technology and quantum physics. But I mean, my company hires back-end software engineers, front-end developers, if they do React or things like that, people who make the mobile applications for your organizations, graphic designers. My team is about 50-50 at Q-CTRL, about 50-50 people who do quantum mechanics for a living and people who build products for a living, right? Who build consumer-facing SaaS platforms and things like that, which makes us quite different than most other organizations in the field. But it does mean that people who have no touch points at all with quantum computing can get into the field from what we do.
Sorry.
Oh, sorry, just one more question.
Right.
Just with the quantum physics, do you see that, just your analogy early on about the first flight aeroplanes and that, you know, manned to the moon at the moment, still using the same technology it probably did 50 years ago, that it maybe opens to a new breakthrough in like a new fuel or a new sort of engine or energy source that'll sort of help, I suppose, man move into the universe or something like that?
Maybe. I think the most exciting way to think about this is to really kind of wipe the slate clean and think about what totally new things you could do if you had access to this kind of new computational tool. Because if you just look any field, medicine, space exploration, whatever, it's really been computing that makes all of those things happen, right? Think about CAT scans, computerized axial tomography. Think about the computer systems that were used in the Apollo missions. So here's my favorite, right? And it's crazy, but it's my favorite. Imagine you solve this problem of making fertilizer. So it's really, really cheap and energy efficient to make fertilizer. Cool. And then simultaneously, you solve another problem. I mentioned that you can do simulations of physics or material science. There's a problem called high temperature superconductivity. Certain materials allow electricity to flow with no resistance. Resistance is what makes your toaster heat up. You flow electricity through the wire. Some of the energy is lost. The wire heats up. This is a giant problem in the way we make power grids. And in the United States, about 5% of all of the electricity that gets sent around the grid is lost in wires heating up. It doesn't sound like much, like 95% efficient, sounds pretty good. But that 5% lost just sending it over wires, the wires heating up, that's more than the total annual generation of electricity in Australia. This is a giant problem. So now imagine that you can solve this problem and figure out how to make superconducting materials that work at room temperature, because right now they have to be really, really cold, and that's impractical. So now you have fertilizer, cheap and abundant. You have the ability to pipe power over long distances with no loss. And now we can totally reimagine the way we build the grid. The information superhighway, sending light over very low loss optical fiber, is why we have, the information age, right? Imagine we had an energy superhighway. Fertilizer, energy superhighway, anywhere you want, on demand. The natural outcome is like terraforming, right? You can turn the desert into arable land. You can have enough energy to do desal near the ocean and pipe that water anywhere you want. Like, it's a totally transformative capability, and it really comes to us only by unlocking these new computational techniques that, solving problems that are otherwise more or less intractable for us. Sound crazy? A little bit?
Sounds good.
Okay.
Other question?
Sorry, this might be one of the dumb questions.
Not at all.
But just to give it a go. So coming from the pharmaceutical industry, now you mentioned that the quantum technology can be used in the chemistry industry. So then is there any applications in the pharmaceutical industry then?
Broadly, yes. There's interest in drug discovery. There are companies, one called Protein Cure with a Q, another called Entropica Labs out of Singapore, that are focused on algorithmic mapping for pharmaceutical discovery. Right? People are actively doing this right now.
Thank you.
Sure.
Two more questions for you. What would you say is the biggest challenge that the quantum community is facing that needs to overcome?
Decoherence, the loss of the randomization. That's why we're so important. I'm selling my own book, obviously. I think we have to we have to weather a quantum winter. I showed the hype cycle, right? And I showed that we're on the innovation trigger and going up to the peak of inflated expectations. There are some things happening in the industry right now that mean we're about to go into the trough of disillusionment for a little while. Some early VCs got in and didn't have the appetite for long-term research. This is the deepest of deep technology. This is the hardest research activity leading towards commercialization you can imagine. Some people don't necessarily have the appetite. We have to, as a community, get through that period when there's going to be some negative press.
Well,
I think there's a gentleman in the back.
You've mentioned a lot about the commercialization of quantum computing, and that's obviously been one of the big backers of sort of Capital or Horizon Ventures. But obviously you showed earlier the ENIAC being its first use to project artillery trajectories. And at the beginning of this presentation, you shared that the NSA is their first university investment into research. Mm-hmm. So, thinking about there's obviously the commercial outcomes of quantum computing, what are the NSA looking to get out of this kind of investment?
Well, I think, the NSA was very transparent about this whole thing, right?
Shock me.
It's true. The NSA more or less just said, we want to know if this is possible. They continue to be the biggest single backer of open university research in quantum computing. And there is no doubt that there is some other stuff going on that they don't talk about, right? We're all grown-ups. But they still fund my lab and labs across the city. They fund labs all over the world. Open research, we publish everything that we do. And I had the very funny experience some years ago. Everybody has heard of Edward Snowden, right? The big leaker in the United States. He's a traitor. Edward Snowden released some giant trove of documents, and in those documents was discussion about NSA efforts in quantum computing. And the Washington Post published an article about this little, 10-page cache or whatever. And it said all these nefarious things about NSA building quantum computers, and they're going to crack your bank accounts and whatever. In that was this very nefarious sounding line. It said, we are pursuing dynamical decoupling of singlet triplet qubits. And I read it and I realized that that's a line item from my contract, right? That was something that my academic program was doing. I wrote to the journalists, and at first they were very excited, and when I told them that it was, from an academic contract, they stopped answering my emails. I think the reality is that, organizations in the intelligence services have obvious interests in weaknesses or potential vulnerabilities of public key encryption systems, probably of exploiting them. But what they are doing right now is funding open university research. And that's something that it does sometimes attract negative attention. I've been questioned about it, but everything we do is in the open, just like, by the way, the Australian of the Year last year, very heavily funded by the same organizations.
Hi.
Hi.
I come from Philips. We make CT, MRI, that kind of stuff. So you mean to say the current future of this hardware, the technology, quantum is going to change how we do CT, MRI, nuclear medicine, that kind of stuff?
Yes. So we do, for instance, Q-CTRL focuses on dynamic control, and the control techniques we use are actually very similar to the echo techniques that are used in MRI and in consoles. We have new control engineering derived techniques that allow you to extract different kinds of quantitative information from MRI. So, I mean, that's a business, part of our business model for the future. Yeah. It's a very exciting area. There's research like that I do on this control engineering side and new sequences. Then there are people who do the development of low field MR using kind of quantum enhanced contrast agents, things like nanodiamond, which can give you an enhanced signal at very low fields. So there's a lot of effort in this area. No research yet. I mean, well, we have commercial products, so if you want to talk. I mean.
There's lots of funds that you can invest in quantum. And, and just speak to Michael about that after the session.
Hi.
I was about to ask that.
Oh, thank you.
Yes, we can talk
How
about
did it
watches
take this
and
long? It's just it's a fun passion of mine that I enjoy mechanical things and I like watches. In particular, there is a kind of watch escapement mechanism called a tourbillon, and a tourbillon it's generally now a bit of watchmaking tech that's just to show watchmaking virtuosity, right? To show very high-end watches would include this. It was developed in 1801 by Breguet, and it was built because at the time men would always wear pocket watches that were oriented vertically. And you know that the way you have a regulation in a mechanical watch is you've got this spring that bounces back and forth, right? Well, if it's always in the same orientation, gravity is always pulling down, and that actually distorts the rate. It messes up what's called the rate accuracy. So Breguet figured out how to make that spring, called a torsion pendulum that goes back and forth, rotate 360 degrees once per minute, right? And so that means what's down is always changing. And that actually dramatically improved the rate accuracy of clocks. That was one of the earliest examples of dynamic control implemented in, at the time, what was the peak of modern technology. My whole career is built on dynamic control. And if I wear a tourbillon watch, I'm wearing my career in metal. And that, to me, is a really deep and profound link to something that's both a beautiful piece of art and, you know, the history of technology. That's why I like it. If anybody wants to see a tourbillon watch, I'll show you later.
And I think that's a beautiful place to leave the session. Thank you so much, Michael. It was
Thank
a pleasure
you.
to have you. I believe you're sticking around for drinks.